Hello everyone, welcome to our low temperature thermochronology online class. We will continue the chapter 4, uranium, thorium, helium thermochronology, analytical techniques. Today we will still focus on the second session about crystal characterization, and the cathodoluminescence technique will be introduced today. Some types of specimens, when excited by electrons, emit light by the process of cathodoluminescence. Cathodoluminescence is the emission of photons of characteristic wavelengths from a material that is under high-energy electron bombardment. Bombarding the surface of a material with some particle or radiation may produce the emission of electromagnetic radiation. This emission can be in a wide spectral range, including the visible range, ultraviolet, and infrared. This general phenomenon is known as luminescence. Generally, the types of luminescence is distinguished by the types of incident radiation or particles and by the kinetics of the emission process. In the former case, photoluminescence is radiation caused by excitation by ultraviolet or visible light, and cathodoluminescence is emission of light obtained by electron excitation. In the latter case, phosphorescence is the radiation that continues to emit for more than 10 to the power of -8 seconds, and sometimes much longer after the incident energy source ceases. And fluorescence is the radiation that ceases immediately within 10 to the power of -8 seconds following cessation of the source. For cathodoluminescence, it is an optical phenomenon excited by high-energy electrons. Cathodoluminescence is neither photoluminescence nor phosphorescence, but it is under the general category of fluorescence. Cathodoluminescence occurs in semiconductors, insulators, be man-made or natural. Solid-state band theory provides a way to explain the luminescence phenomenon. An insulating solid material can be visualized as having a valence band and a conduction band with an intervening band gap. If a crystal is bombarded by electrons with sufficient energy, electrons in the valence band are excited into the conduction band for a brief time. When the energetic electrons attempt to return to the ground state valence band, they may be temporarily trapped on the scale of microseconds by intrinsic structural defects and/or extrinsic impurities traps. Subsequently, these electrons recombine with the holes left in the valence band. The energy difference is released as a photon of wavelengths of light. The various band gap energies with their respective wavelengths and colors is shown to the right figure. Most of the wavelengths fall within the visible range, sometimes extending into the ultraviolet or infrared. Many minerals emit cathodoluminescence, including diamond, quartz, zircon, and calcite, and so on. Localized energy levels in the gap between valence and conduction bands arising from lattice defects. Interstitial ions or substitutional impurity atoms often play an important role in the cell emission. Substitution of an element for the usual one is believed to be a key cause of distortion of the lattice in the mineral. The impurities in the structure generate luminescence centers and are most commonly transition elements, rare earth elements, and axonite elements. These impurities are generally the most common source of Cl in minerals. Certain elements behave as activators that promote Cl emission in minerals, small concentrations of which are sufficient to produce Cl. A few elements can perform the opposite role, modify the energy level arrangement so that the Cl process doesn't operate or is diminished. These are quenchers. The most common quencher in minerals is typically ferrous iron. A given mineral can accept different activators and give out a different Cl color for each. For example, feldspars can accept manganese iron to give greenish yellow, and ferric iron to show red. A given activator may be incorporated by different minerals and produce different colored Cl in them. Various materials emit Cl, including many minerals and semiconductors. In semiconductor physics, analysis of the emitted light can be used as a characterization tool. Now is the question, how to see the Cl light? There are two distinct methods to image this effect. One is by a scanning electron microscope or microprobe equipped with a Cl detector, which we call SEM-Cl, like this. And the other is by a small attachment to a petrographic microscope, which we call optical Cl, like this. Cathodoluminescence occurs in a range of different minerals and is caused by either crystal structure defects or trace elements. Cl images can yield valuable information not easily seen by other means. Cl images will play a useful petrographic role alongside backscattered electron images and light microscope. For quartz, it gives rather low Cl intensity, but since neither backscattered electron images nor secondary electron images generally provide useful information, SEM-Cl has a particular significant role. Comparison of these images shows that SEM-Cl analysis reveals unique textures in vein quartz from the porphyry copper deposits. SEM-Cl image shows that at least 2 generations of quartz are present. Cl dark quartz and pyrite field fracture in Cl bright quartz that was precipitated during early hydrothermal event. This difference in luminescence couldn't otherwise be detected by backscattered electron image due to the grains having the same mean atomic number on light microscope. Transmitted light image shows that 2 generations of quartz visible with SEM-Cl are optically continuous. For plagioclase and orthoclase, cathodoluminescence images provide a convenient means of identifying these minerals. There are greater compositional variations amongst feldspars, giving rise to a range of Cl intensity and color. Cathodoluminescence images of zircon commonly show considerable detail related to growth processes. Since the Cl emission is at least partly dependent on compositional variations, typically involving rare earths and yttrium. Although backscattered electron images usually show similar general features, Cl images often reveal finer details. Cathodoluminescence images are used to characterize zoning patterns of zircons and different groups of detrital zircons in sediments. As shown in the right figure, the 2 innermost zones in the fluorapide grain may be indiscernible in backscattered electron image, but visible using Cl image because of different amounts of rare earth elements and/or manganese in the fluorapide structure. That's the lecture today. Thank you for your attention. See you next time.